In America, there are real secrets. They lurk in the darkest forests and in our most ordinary towns. Between the earth we see and the ground we search, there are doors. And when they are opened, geophysics becomes reality. I'm Carolyn, and this is Unearthed Secrets. Hey everyone, I'd like to invite you to my homogeneous half space. It's got everything we need. The ground is homogeneous or homogeneous, depending on your level of pretentiousness. That means that the ground material is uniform throughout. No differences in ground character here. Well, hey there, Harold. Welcome to my homogeneous half space. Let's check out an example of uniform ground with some dirt. Check out that uniform dirt. It's all the same. I'm not really sure what's happening here. I think I'm just going to go back to my half space now. It's a half space because we're concerned with what's happening in the ground and not above it. Oh, hey there, little buddy. What are you doing in my half space? Oh, making it uniform, I see. Thanks. And now for the physics of geophysics. Voltage is the push of electric energy to electrically charge and move particles in the ground. Hey, look at that! They're measuring voltage! Ah, yes. You need 3 guys on that. 1 to hold the contacts, 1 to hold the voltmeter, and 1 to point at it. Good work, guys! Voltage is like the pressure push that gets the current moving. Current is the net rate of flow of the electric charge through the ground. Now let's begin moving that current through the ground. How does that sound, Harold? Excellent. Moving a current through the ground will allow us to eventually determine the resistivity of the ground, and that's our goal. The current flows radially away from the electrode in a half-sphere or hemispherical way. These hemispherical locations in the ground are called equipotential surfaces. Each circle represents a location where the current is distributed with the same value, changing as the distance from the electrode in the middle increases. Are you having a hard time picturing a hemispherical shell that has the same current value along the surface of that shell? Here you go. Each one of these has the same current that changes as the shells get bigger. How's that? Uh-oh. Well, it's not really important for our discussion. Just know that the curved surface area of a hemisphere is 2 pi r squared. That shows up later. Now that you know how the current gets started, let's take a look at the components of the ERI survey. The injection electrode is labeled A. This is where the voltage from the instrument box begins the current flow in the ground. This electrode is the current source. Notice the current flow lines in yellow and the hemispherical shells with uniform current distribution. What? No! How are you doing, Harold? Oh God. Okay. Injection electrode B is located where the current in the ground travels to complete the circuit with injection electrode A. The current exits the ground system here at this location, called the current sink. These 2 electrodes are where the voltage is measured for the resistivity calculation after the current travels through the ground. This configuration of A, B, C, and D is called the Wenner array. You can move the 4 electrodes around in different ways to obtain data in a way that fits your needs. I used the dipole-dipole array at the Amber-Crum property. A and B are on the left, and C and D are on the right for the dipole-dipole array. The Wenner array is simpler for example purposes, so that's why we're using that one here. What? Oh, come on! Resistance is the ground's opposition to the flow of electric current. Ohm's law shows the relationship between voltage, current, and resistance. Resistance and resistivity aren't the same thing. Resistivity is the inherent property of a material that measures how strongly it resists electric current. Resistance depends on how much ground we measure through. It depends on the cross-sectional area that the current passes through and the length of travel. That makes things a little hard in the field. Since resistivity is a characteristic of the ground itself, it's easier to solve for resistivity instead of resistance. Here, let's travel to a dirty drainage system so I can better explain this with soiled water runoff and a sewer. The voltage here is represented by the higher pressure on this side of the sewer hole, where the water is flowing, because voltage is the pressure push. The electrical current is represented by the water flow, or how do you say, water current? The resistivity of the technically fresh, yet dirty and grassy water is probably around 10 ohm meters, assuming the water is equally gross, dirty, and grassy uniformly throughout. No matter where in the system you look, it will always be 10 ohm meters. If I filled my swimming pool with this water, it would still be 10 ohm meters. However, the resistance of the water current here depends on the size of that there sewer hole. The resistance would be less if the hole was bigger, and more water would be able to flow through. The resistance depends on the size of that hole, but the water's resistivity is still 10 ohm meters, no matter the size. We can rearrange Ohm's law to solve for resistance. I know, we don't want resistance, right? Hold on. Divide both sides by the current and you get voltage over current equals resistance. We can take Ohm's law and substitute resistivity into the equation in place of resistance. There's a longer mathematical way to show how this is done, but I've opted to omit this for now. To get resistivity, we have to multiply the right side of the equation by the geometrical factor k, or kappa? I'm not sure if that's a kappa or not, but what does this mean? K, or kappa, represents multiple values. Remember my hemispherical shells from earlier? After a little math, we end up with 2 pi r for this type of electrode array configuration. K is slightly different for other array configurations because of the electrode spacing and arrangement. Here, r neatly becomes a, which is just the electrode spacing. So, we multiply 2 pi and the electrode spacing by the voltage divided by the current. That gives us the resistivity. So let's turn on that Siskel Kid Switch 24 and collect a data point with the Wenner array. We have our yellow current flow lines going from the current source electrode to the current sink electrode. When electricity spreads out, it follows a curved path in the ground. It's not practical to look at the voltage value at either electrode C or D for a calculation of the resistivity of the ground when searching for anomalies. These voltage values are difficult to measure. Knowing the voltage measurements at electrodes A and B, we can determine measurements at C and D, and thusly calculate a measurement for the difference between those two electrodes. This gives us a proper voltage measurement for calculation of resistivity in the ground in the middle of these electrodes. Each set of 4 electrodes, the source, sink, and 2 measurement or receiving electrodes, provides one resistivity data point in the ground in the middle of the electrode setup. The equation that stems from Ohm's law with resistivity and the geometrical factor in place of resistance now has the difference of voltage between the 2 receiving electrodes instead of an absolute voltage measurement. This provides a resistivity value in the ground in the middle of the line with high accuracy. To collect more data points along the survey line at the same depth as the first data point, we keep the spacing of the electrodes the same and just move everything down the line by 1 electrode. Keep doing this after every data point to receive a new data point. The Cisco Kid Switch 24 automatically changes electrodes, so we don't have to do this manually in the field. To collect data points deeper in the ground than what's shown here, you need to increase the electrode spacing. Make A equal 2 meters instead of 1 meter for a deeper data point. Then make it 3 meters for an even deeper data point, and so on. Collecting these individual data points won't give you the final resistivity image of the ground, though. Some areas of the ground contribute to multiple data points during the survey as the current passes through them during different data point collections. So there's a lot of information that can be obtained from these individual data points about the ground along the entire survey line. The individual data points are put into software called inversion software. It basically says if these individual resistivity data points, called apparent resistivity values, were all collected, what must the ground look like to create these individual data points? It runs this through a computer algorithm and produces an image of what the resistivity structure of the ground must look like to achieve those individual values. What you're looking at is the final resistivity image that represents the resistivity structure of the ground at the amber crumb property. The top image is one survey line of 24 electrodes. The bottom image is zoomed in on a particular part of the survey line. Once we know the next step in Amber's case, I'll share more information about the results of the ERI surveys for Amber's case. How are you two doing? Well, at least he looks happy. How are you doing, Harold? Excellent! An interpretation of the ground can be done by comparing known resistivity of different soil, sediment, and rock types with a final resistivity inversion image, like the one from the amber crumb survey line. If we're looking for an object, we can assume resistivity character based on water content and probable void space within the object we're looking for. I'll go into more depth on that in another video. Thanks everyone for watching. Like, subscribe, comment, and share please. And click on that notification bell. Okie dokie, see you later.